So basically, previously couple classes I tried to explain to you the way the press, the plate and frame filter assembly has been put together, has been designed and put together, and I have a summary slide which is up here. So let us quickly again go through the design. The black vertical slices, they represent the plates, which are, I said, solid rectangular or solid square cross section. Then the between two plates is the white vertical structure, that is the frame, which is of the same dimension as the plate with the same X area, but it's hollow, it's empty. In other words, it gives sufficient space for the solids to accumulate, because as you pump a slurry which is containing solids, we have to design the press in such a way that we give adequate area for the filtration and adequate space for the accumulation of the solids. So the filter medium I explained to you is enveloping each black structure here, that is the plate. So it's on both sides of the plate, the cloth or the filter paper or canvas, what have you. And there are two ducts on top and bottom. So you put the slurry and it's pumped, and now you pressurize the plate and frame series assembly, okay, say by mechanical means or pneumatically. And now when you pump this slurry, the fluid will distribute itself through the white spaces, and it will also contain the slurry, and the solids of the slurry will start accumulating on the filter medium, the cloth or the paper or the synthetic material. Okay, and gradually the resistance that these solids, as they accumulate and increase in thickness, they will offer greater and greater resistance, and so the filtration rates will go down as long as we keep the delta P across this assembly fixed. Okay, obviously if I start pressurizing it more and more, I can get higher and higher rates even with the passage of time, but for the moment we said that we have a constant pressure filtration. And so of course, as the resistance due to the accumulation of the biomass of the filter cake increases in thickness with the passage of time, then resistance will increase. And what I explained to you is that this resistance we can again model exactly by the principles that we have used earlier by Darcy's law, because a very simple form of the Darcy's law, if we look at it, we can explain it. For instance, the Darcy's law related the flow rate through a bed of solids, right, and to the pressure drop. So here again we have a pressure drop, we have a flow rate because we are pumping slurry. So if small v were the velocity, this delta P was the pressure drop across the assembly, L was the thickness of the bed, mu was the viscosity. Basically the simple form of Darcy's law would give us that small v, the superficial velocity, is k times delta P divided by mu times L. That is, k is the Darcy's constant, delta P was the pressure drop, mu viscosity of the liquid, and L was the thickness of the bed, right? So if I were to just recast that and write it as such, velocity is just delta P per unit, delta P upon mu whole thing divided by L by K, then L by K that is the length divided by the Darcy's law permeability, has units or dimensions of resistance. And in other words, this resistance can be written based on the characteristics of the filter cake. Okay, so that's what we have to do. So this L by K term in the Darcy's law, V is equal to K times delta P by mu L. This L by K term is resistance. So I think I gave you an simple expression taking the Karman-Kozeny equation. So let me just check where we were. Yeah, this was the cross-sectional area of the plate and the frame. I hope you can see it. The black one is the plate, the white hollow one is the frame. And as I told you, they are all assembled one behind the other in series, right? And the number of plates and frames depends on how much volume of the slurry you are pumping, right? Or how much load you are putting on the system, right? Or the throughput that you need to get. Okay, so that I explained to you. Then I went to this more elaborate form of Darcy's law, not just the V is equal to K delta P upon mu L, which I just used right now to explain that L by K term is like a resistance. And I derived, yeah, we can do it for any arbitrary shape. I showed that, yeah. So if what I used small v was the velocity, so we can write that as 1 by a times dv by d theta, where theta is time. Capital V is the volume of the slurry that we are filtering, and A is the filtration area that we are giving, right? So that can be written as shown here. Yeah, that can be written as minus delta P upon alpha mu W capital V by A. That's what I showed you, and I explained what these terms were. So again, capital V is the volume filtered, A is the filtration area. Small w I defined based on slurry properties. So that was weight of solids per unit volume of liquid in the feed slurry, right? So I defined that. So if you know how concentrated your slurry is, you can always find what what small w will be, because you can take, if you take 100 uh, grams of slurry, you can find how many weight of solids are there in that slurry. If you know the fraction, mass fraction or whatever, so weight of solids in the slurry per unit volume of liquid in the slurry. So it's some kind of density, effective density, you can say, right? So small w you can find. So I explained that mu was the liquid viscosity, and alpha I defined as the specific cake resistance, which was given as follows. Wait a minute. It's not going left or right. It's only going forward, not going backwards. Very funny. So if you see how to get back to that, well, that's the final equation. But what I wanted to tell you how to derive that, that's not a problem for me. But then I can't get to that slide anyway. So what I showed there is that the 1 by 8 dV by dt I explained to you was delta P upon some alpha into small w into V by A into mu, right? Okay, and alpha was defined as the specific cake resistance, which could be defined for any arbitrary shape, where because it came in terms of specific surface area S naught, and it of course included all the epsilon terms that we have been working with all through the course, right? So that's again a material property of the cake, and so you can always find that. So the only thing I said is that this resistance term, which was L by K in my simple Darcy's law formulation, that equation that I gave you last time only included the resistance as the cake is accumulating, right? So this alpha times mu times small w upon V by A is a measure of the resistance that the accumulating filter cake offers to the flow. Okay, so basically what it means is capital V by A is like a thickness. It's like a thickness. Alpha is some material is like you can take it if the cake is incompressible. That is that as the cake keeps on increasing in volume, you can't compress it or squish it. In other words, the V by A is a true thickness, and alpha can then be taken as a constant. Okay, small w is a constant, mu is the material property of the liquid, okay, of the slurry. So it's depends directly proportional. That means what we are saying is the resistance that is offered to the flow is directly proportional to the thickness of the cake, V by A, capital V by A, right? But what I told you is that that is a bit of an approximation, because I said that every filtration problem not only has this variable resistance, it's a variable resistance because it's increasing with accumulation with time. Um, that is, as V by A keeps building up, that is the thickness of the cake keeps building up. But I said that there is also a constant resistance. Let us say we were working with a fresh press before anything has accumulated. You can't say that the resistance to flow is zero. Okay, there are a large number of flow pressure drop due to the piping. There is also the gauge. There is also the filter medium itself, right? The canvas or the cloth, or so all of them also offer resistance. But we can idealize that and say that all of those parts of the equipment, the piping, instrumentation, and the filter press medium itself, it offers a fixed resistance. Okay. So if the resistance that I put earlier was variable and increased linearly with thickness for an incompressible cake, this resistance is fixed. So L by K is some constant resistance R constant plus a variable resistance R variable, which I gave you as directly proportional to capital V by A. Am I clear? So what I have done in the slide, which I am not able to reach, it's somehow not going back somehow. Let me try once more. Is I took the term 1 by 8 dy by dt or dv by d theta. That's the left. That I kept that the same. That was delta p in the numerator. That's also the same. And the term we had was mu times alpha times small w times v by a. So what I have done is I have written that as I have taken mu out of brackets and written that as mu within brackets alpha w capital V by A plus an R fixed Rm term of for medium and bracket close. So in other words, the equation that is there on the slide that is not somehow showing up, but is there in your slide collection is 1 by dV by dt is minus delta P upon mu, and then within brackets alpha times W times V divided by A, then a new term plus a fixed resistance Rm due to the medium. Bracket closed. Okay, that's the equation that was there in the slide. So now, what are the units of Rm? Rm has if you analyze, you will find Rm has dimensions of length inverse. So it is like meter to the power minus 1. And I gave you the physical significance of Rm, that it represents the resistance of the filter medium and piping to the flow of filtrate. Okay, it's the combined resistance, fixed resistance of the medium piping instrumentation to the flow of filtrate. Now, the problem is that the V by A term is directly proportional to length. It has a length scale of length, and the Rm term is length to the inverse. So you can use it, but it was filtration people don't like to use it in those terms. So what they said is, we want to write the filtration equation, which is what we are trying to derive, in such a way that the two resistive terms, one the variable resistance due to the cake accumulation and the fixed resistance due to flow of filtrate due to the piping and filter medium, etc. I want them to be in the same dimensions so that I can compare. So in other words, if the flow of filtrate is capital V, and let us say that there was an additional flow that would be required due to the resistance of the fixed resistance, and we call that V effective, which is capital VE. Okay, then by comparing, if I can add the two resistance Rm plus R variable as represented as capital V plus VE, then this VE term, if is very small compared to capital V, then I can neglect it, and then both would have the same dimensions of volume. Okay, so the equation was written as 1 by A dV by dt is minus delta P upon mu alpha W by A, and within brackets capital V plus V subscript E or V subscript effective. Right. So what is the meaning of this VE? This VE is the volume of filtrate which is required to build up a fictitious layer of filter cake, okay, but one whose resistance is equal to the resistance of the filter medium, piping and instrumentation between the pressure gauges. In other words, what you are replacing Rm, the medium resistance, fixed medium resistance, is by a equivalent volume of filtrate V subscript E, and you are taking that it is the one, this volume is the additional volume over the volume you are filtering, capital V, in a time theta. This is the additional volume that is necessary to build up another layer of filter cake, which is a fictitious layer, let us call it. It doesn't really exist, it's in our thinking. The resistance of this extra fictitious layer is equal to the resistance of the fixed resistance of the system. In other words, you are dividing the total resistance into these two terms, but now you have recast them in volumetric terms, so that if you could find a way to evaluate VE or V effective, and if it's very small compared to capital V, you can neglect the fixed resistance. However, if V is not very small, let us say it's more than 10, 15%, 20% of it, then of course you must consider both of them. So The general filtration equation is the one that is given 2 slides before. So 1 by 8 dV by d theta is minus delta P divided by mu alpha W by capital A, and then open brackets capital V plus V effective, bracket closed. Okay. Now, what this slide that is there shows is the integrated form of the differential equation, filtration equation that I just showed you. How has the integration been done? We needed to make some idealizations. One is, we said the pressure drop is constant. So delta P is constant. So it's a constant pressure filtration, right? And we have assumed that the cake is incompressible, which means that whatever be the delta P, this alpha is constant. You are taking the specific cake resistance to be constant. If the cake were compressible, then this alpha would be direct function of the pressure drop delta P that you impose between the plate frame assembly. Okay, but for the moment we are taking the filter cake to be incompressible. So basically we can then integrate that general differential filtration equation by separating the variables. I have a slide on that also, and then putting in the initial condition. What are the initial condition? At time t equal to 0, there was no filtrate, so V was 0, and at time equal to theta, we had a filtrate of capital V. So we separate variables, and then we have integral 0 to capital V to V plus VE dV is nothing but integral 0 to theta A squared into minus delta P within bracket upon mu alpha W, which are all constants for the incompressible system, d theta, and we integrate from 0 to theta. So then when you integrate that, the V dV term will give you the quadratic, which is the V squared by 2 term on the right hand side. Then you will have a product form of the V effective times the V filtered, capital V into VE, that is the second term in the brackets on the right hand side, and of course all the constant terms, which is the mu alpha W times the square of the area and the fixed delta P for the constant pressure, and the theta is the time of the filtration. So this is the time necessary to pass any given volume of filtrate, and this particular equation calculates it. Now, what I want you to look at this equation is, suppose we had found this is the general filtration integrated form for constant pressure filtration. And now suppose you had a way of finding, see, you will have to find all these constants, no, mu alpha W, a specific cake resistance you will have to find, right? It's something that it depends on the filter slurry and properties, right? So you don't know it a priori, so you have to find alpha. W you know, mu you know, capital A comes from the way that we have to discuss what capital A is, but let some form of area that you are giving for the filtration, delta P you can measure. So alpha is unknown, and V capital E is unknown, V subscript E is unknown. So suppose we had a way of finding all of these. Let us say V subscript E was very small compared to capital V. I said that you can neglect the product term here, VE into V on the slide. Right? So if we neglect it, then we are left with a reduced integrated filtration equation for constant pressure filtration in an incompressible cake. The theta is just mu alpha W upon A squared minus delta P within bracket, and then bracket open V squared by 2. So this is the quadratic form, very well known form of the filtration equation. Now what I want you to do is, please take a look at the either differential form or integration form or whatever form you want to see, and give me a way to determine alpha, the specific cake resistance, and V subscript E, which is the measure, which is a measure of the fixed resistance of the system. Please find a way to, from a set of data, to calculate these parameters. So how will you essentially linearize this quadratic or product form, and how should you plot it, and how are you going to get these parameters? So can you please think on that? So that's the thing I want you to work on. Of course, so many possible extensions are there now. Now, suppose I were to, we may not be able to do it today, but suppose I were to say alpha is not constant, it's not incompressible, and alpha is some specific measure of delta, some function of delta p. I can put that function into your differential form of the general filtration equation and again reintegrate. I will have a new theta term, and again I can check, is VE very less than V, if I have a way of evaluating the parameters. If it's less, then I get the quadratic form, but with some different constants, because now alpha was not constant. Of course, I have to know how alpha changes. That is one extension that we can think of. Other extensions are also possible. Right now, I assume delta P constant, but let us say delta P is not constant. But suppose I say I want constant dV by d theta, that is rate of filtration is constant. Then how will this filtration equation look like? Anyway, so those are the types of questions that we can ask. But my basic point was to derive for you the differential form using the basic Darcy's law, the differential form of the general filtration equation. Of course, right now it's for constant delta P across the plate frame assembly and incompressible cake, and then I have the integrated form. Now what I have asked you to do is to come up with a formulation which determines the unknown parameters, the specific cake resistance and the fixed resistance V subscript E in this system. There are many ways of doing, there's no one way of doing it. What could be some possible ways of obtaining these unknown parameters? Okay, I will indicate one method. Suppose I were to take the differential form of the general delta P constant filtration equation and invert it, then I will get a reciprocal filtration rate d theta by dV, right? Now I can measure this at every interval of time, right? I mean, I can collect the filtrate, I can see how much time has elapsed, and I can have a rate, I can have a differential rate, right? So that's a measurable thing. If I were to plot that, or if I were to study its variation with the volume of filtrate that is collected as time passes, and if I were to plot that, then I will get a linearized, I'll have a linearized equation. So if I were to take d theta by dV and plot it versus capital V, then basically the quadratic form that V squared will just be, it will become V plus VE, right? And I differentiate it, and so I will get a slope which is nothing but mu alpha W upon A squared into minus delta P. That's the slope. And so if I know the slope, then I can always find alpha, right? Because all other things I know. And then what is the intercept of this in this formulation? It is a linear form, so the intercept then will be whatever was the slope, mu alpha W upon A squared delta P minus delta P times VE, right? So slope into VE is the intercept. So by finding that slope you an intercept, you will be able to get VE also, and you can check is VE very much less than V, and whether you have to use the both the terms in the integrated equation or not. That is one way. So essentially, another way what you can also do is that if you were to take the, instead of taking the differential reciprocal filtration rate, you can cumulatively find the time theta, multiply by A by V. That is something you can find, and then plot it versus V by A. And that also will give you a straight line, because the AT by V is equal to some constant into V by A plus another constant. So this slope then will be the mu W alpha upon twice delta P, and then intercept will be mu into the VE upon delta P. So that is another way of finding it. So it should be possible for you to find the parameters of this system. So what is it that we have done? I started with the description first for the describing how the equipment looks like, something which we didn't really worry about in a simple sedimentation experiment, because the equipment didn't have much per se. And for this rectangular setup, I showed to you how to apply Darcy's law and obtain the filtration equation for an incompressible system. Now, what I want you to think is, how do I extend this to compressible cakes? A harder question. Second thing, what I want you to think is, here capital A, can I take it to be the geometrical cross-sectional area of the plate or frame, or should it be something different? It will be some proportion, it will be proportional to that, surely, but is it identical to the geometrical area, this capital A that we have to use along with this filtration equation, either in differential form or integrated form, what have you? What is that A? इस पर आप सोचिए. Okay, so that is something that I would like to answer the next class, and then let us try to solve some problems. That's something that we have not been able to do. Let us take some interesting problem, and I think I would like you to give it a try, and that will also explain to you why we take capital A as the way we, I mean, as I said, it's not exactly equal to the geometrical area of the plate or the frame, or the cross-sectional area of the plate or the frame. And then some design things also will get explained. So maybe we can try some model problem. So that is something, but before that we have to worry about also extending it to compressible systems. And as I said many times, delta P need not be constant. Then what should we do? Those are some of the harder questions. Okay. So can somebody guess? See, look at can somebody guess what capital A we should take to exactly get the correct answer to the parameters in the system and correctly get the filtration, predict the filtration time? If you look at the plate and frame assembly, you may get a hint. You see, there is a series of plates and frame. However, when you put the filter medium over a plate, that filter medium covers both the left side of that plate and the right side, and both of those faces are interacting with the open frame on either side of that filter medium. So given that type of arrangement of the canvas or the cloth, what would you think should be the appropriate capital A to use in the equation that is there on the screen? That is a good way of putting it, and it may give you some clues as to what we should use. Okay, so please think on all of these, and I shall answer you on Saturday. And moreover, Saturday, then let us try some problems, and then we have to do all these extensions. It's going to take us at least 2 more classes. And then from 22nd, we will try to, if whoever wants to present, somebody has to set the ball rolling, because I think we need to get a move on that group project, and we can take 15 minutes per group of 6 or so, and we need 4 classes for that. All right, so what is it that we have done? We have applied Darcy's type law to a new process of filtration. Again, we did not limit ourselves to spherical particles, but to any regular shape, something that we have done in other fluid solid processes. And I derived you a general filtration equation in differential form as well as in integral form, and I explained to you how the parameters of the specific cake resistance and the fixed resistance of the system can be evaluated. I think we should discuss that further and then apply it to some particular problem, so that at least the constant pressure, maybe we can keep pressure constant in that problem. And then we should extend it to cakes that are not compressible, but still the pressure, and which that's one. Second, we need to look at other forms, new forms of the general filtration equation when delta P is not constant. So these are, and this all is going to take us at least 2 classes. Okay, if not 3. Okay, so this is the way, and meanwhile, you will gear yourself up for your presentation, so that around 22nd, we are ready to start. All right, any queries? Then I'll be happy to answer. I mean, I don't know how clear it is presented, but if you ask a question, then yeah, I should be able to answer you. Otherwise, it's okay. The recording is available and others can listen to it. The slides are also there. That should be quite accessible to everybody. All right. Okay, we will continue on Saturday and try to complete this thing by next Wednesday. Thank you.